So 10.7, the idea of partial pressure. 10.10 is a little stoichiometry with gases. And thermal energy transfer is these examples. And then calorimetry, which is the lab we just did. It should look familiar. It's number 66. So let's go over these. I believe that's the last of what's going on test 3. This coming Monday, I'm going to do makeup labs. So if you need to make up any labs, that'd be the time to come. Then when we get back from break, we'll have a Monday and a Wednesday. This Wednesday will be our test. And I guess this Monday we'll do review.
Are you going over these today? Or okay, so these today
And then that'll be it. Makeup lab on Monday.
If we don't have any labs,
And you don't have to come. Review there. And then the final is next. The next week is final.
it's going to be, are you still sure it's going to be 12 hours every 30?
I think I can do, Tuesday and Thursday. Most people want it on Tuesday, but I think I can offer it on Thursday as well. Okay, let's go over these. Partial pressure. Okay, you guys listen up. New material. Guys. Okay, the information we're given is and I'm going to say pressure total. Total pressure is this. And pressure coming from CO2 is 112 millimeters of mercury. This is a simple concept. Argon, pressure by argon is 225. Pressure from O2 is 114. And mercury. And it's saying there's also some helium in there, and what's its partial pressure? A couple other facts. There's the mass of helium in there. Mass of helium gas present 12.0 liters. This is all the information we're given. Partial pressure just means this. We've got CO2, argon, O2, and helium all together mixed in a chamber. The chamber is at this temperature, and this is the size of the chamber, the volume of the chamber, and this is the total pressure in the chamber. So the simple concept is these just simply add up to the total pressure. So you could do a simple subtraction here to find out how many millimeters of how much pressure is coming from the helium. You just subtract from this 112 and then subtract 225 and then subtract 114, whatever's left. What I'm saying is, to be a little more explicit, pressure coming from the CO2 in there, plus the pressure coming from the argon, plus the pressure coming from the O2, plus the pressure coming from helium equals the total pressure, which is 745. So all you have to do is subtract all of these from here, whatever's left, that's the helium. Simple, right? You guys get that? So if I do this, 745 minus 112 minus 225 minus 114, what I have left is 294. If it asks for the partial pressure of helium, I'd be done, that would be the answer. But it's asking me what is the mass of the helium. What you can do is use PV equals nRT. With this, find the moles of helium, and then from that, calculate the mass of helium. Meaning, I can use the partial pressure here of helium, this. So, partial pressure of helium, 294. Here's one other thing we need to do. Put that in here yet? Hold on. There's 3 PowerPoint in here. I should put, the conversion. So we're going to convert to atmospheres. We're going to convert this to atmospheres. And that way we only have to use R equals 0.08206 liters atmosphere Kelvin. Okay, that's good. So first I'm going to go 294 millimeters of mercury, and then 760 to 1 atmosphere, and that'll convert us to atmospheres. So 294 divided by 760, and I get 0.387 atmospheres. So now we can do PV equals nRT. Partial pressure helium in atmospheres, 387. The volume is 12.0. N is what we're looking for. R equals 0.08206 liters per atmosphere, all Kelvin. Temperature is already in Kelvin, 273 K. So just to solve, so divide both sides by R and T. So now I'm just going to solve for N. Temperature 273.387 times 12 divided by 0.082006, divided by 273. So that's how many moles of HE I have. You with me?
How did you get the conversion factor from,
It's on there.
oh, okay.
It's the weird one that says, so that's inches. The floor is the same thing, it's 1 millimeter of mercury,
Oh, okay.
so don't miss that.
So then, do we get that, chart on the test?
Yes.
Okay, thank you. Where did the R come from?
Where did the R value come from?
Did you read that original problem, or?
They didn't mention it in there, but I'll give it to you on the test.
Okay, is it just a constant?
It's a constant, it's always the same. As long as we're in liters, atmospheres, and moles, and Kelvin, then we're good. There is another R value that uses millimeters of mercury,
Okay.
and it would come out the same. But the way I'm teaching you how to do this, we'll just always convert to liters, atmospheres, moles, and Kelvin, and then we'll always use 8.08206. Okay, I'm almost there. That many moles of HE and 1 mole of HE is 4.00. So just multiply by 4, I guess. 0.207 times 4. So that's the mass of helium in that mixture. You guys follow that?
Yes.
Partial pressure. And one variation on that. Oh. Mole fraction. Still a simple concept. Just do 7 feet. Let's not do 74. Okay, the gas mixture contains 0.5 grams into grams of O2 in 1.35 liters, 15 degrees C. Calculate the mole fraction and partial pressure of each component in the gas. Okay. I need to convert this to K. And liters is good, so 288. That R. R we have, temperature we have, volume So we just do this. So N2, there's two N's. It's going to be 1401 plus 1401.
It should be greater
Say again?
than, should it be greater than 72?
Yes. The grams will be 28.02 grams of N2. So 1.05 divided by 28.02. O2, and that's going to be 32 grams of O2. 1.35 divided by 32. All right, mole fraction. They always use this fancy X, at least most books do. Total number of moles. X moles of N2 plus X moles of O2. And mole fraction is just this. Let me do this. N for moles. N for moles. N for total number of moles. So mole fraction of N2 mixture is you put the number of moles of N2 on the top. I'm missing a figure there. 105 divided by 28.2. 03. 1.05 divided by 28.02. 375. I've done 375. So we calculate that over the total moles. The total number of moles there is this plus this. 0.0375 plus 0.0422. So that's the total. So that just goes in the denominator. Oh 0375 divided by 0.0797. Mole fraction of N2. And for O2, O422 divided by 0.0797. So there's the mole fractions. Again, it is a simple concept. Does that make sense to everybody? Mole fraction. Similar to partial pressure. Okay, now it wants the partial pressure also. And we'll just use these. And missing something. I'm gonna get confused, I'm just gonna skip it. Okay. Partial pressure, okay, these. All right, so you're given chemical reaction, H2O, H2, plus O2. And I guess it's significant here, these are gases. That's all right. And you're asked, what mass of H2O is required to O2? 3105K for temperature, 0.981. Okay. So what we have is, we have our liters defined, temperature defined, atmosphere is defined, we have R. So we're just going to find N. Find N for O2. So I'm solving that for O2. Pressure is 0.981. Volume 1.85. R is 0.026. Temperature is 350 K. 981 1.85 divided by 0.206 divided by 315. So that means that's how many moles of O2 will be there if all this is true. And then you're just going to go 0.0702 moles of O2 mass of H2O. Moles of O2, and so it's 1 mole of O2 to 2 moles of H2O. And then the last thing is 1 mole of H2O. It's 18.02 grams per mole. That'll tell you the grams of H2O you need to get that many liters. Step 1 is that. Find N using PV equals nRT. And calculate this out, 0.0702 times 2 times 18.02. That's the mass of H2O that's needed to create 0.185 liters. Follow that? What else we got? It's 90. Two. Two gives us 4 aluminum plus 3 O2, 8 L2O3. This is a gas, this is a solid, this is a solid. All right, the question is, what volume of O2 at 782 millimeters of mercury 25 degrees C reacts with 3.2 grams. This time we're just going backwards, and we're going to need to turn this into atmospheres, and this into Kelvin. 782 millimeters of mercury, 760 millimeters of mercury is 1.0 atmospheres. 782 divided by 760, so we're at 1.03 atmospheres. That 273.15 plus 25 equals 298. Those two, we have our so we have temperature, we have pressure. What volume is what we're looking for? We have R equals moles. To find the moles, we're going to go 53.2 grams of aluminum. Aluminum is 26.98. And now our mole ratio, 4 moles of aluminum to 3 moles of O2. And that's going to give us the moles of O2. That's going to give us this. And then we'll use PV equals nRT to find the volume. 53.2 times 3 divided by 26.98 divided by 4. 1.47 moles of O2. So it's PV divided by R, T equals N. Pressure, 1.03. volume is what we're looking for. Hold on. So I want to go volume equals nRT. Volume. So volume is N is 1.48. R is 0.08206. Temperature is 298. Pressure is 1.03. And that equals 1.48 times 0.08206 times 298 divided by 1.03. And that's going to be in liters. That's it. So it's just backwards from the one we did before. You guys okay? And there's another one. Four. Can I erase? The reaction is 6 lithium is into yields. I won't say STP on the test. Standard temperature and pressure is, standard temperature is 298.15. I can't remember, they changed the standard at some point. Before we used 20, 273.15, it's 20, I think we used 20. So pretend that this just gave me 283 for temperature. So temperature is 283 K, 293. And standard pressure is 1 atmosphere. STP means standard temperature and pressure. This is standard temperature and pressure, but I'll just give you a pressure and a temperature on the test. But just for an extra example here, we've got that. Okay. Liters of into, I do have to turn this into liters. Just do that. 58.0 divided by 1,000. Got that. Now we can solve for the moles using PV equals nRT. N pressure is 1, volume, oh, that's the volume. Pressure, volume, bar 0.08206. Temperature is 293. So the number of moles is 0.0580 divided by 0.08206 divided by 293. Now that we have the moles of N2, .00241, mass of lithium. Mole ratio is 1 mole to 6 moles of lithium. And then 1 mole of lithium is 6.94 grams. So what mass is lithium? So that's going to do it 0.00241 times 6 times 6.94. So stoichiometry with gases. You're either using PV equals nRT and then using the mole ratio and the grams per mole, or you're doing it the other way around, depending on what you're asking for. Okay, thermal energy transfer. This is 1, 2, back up to this previous chapter. I'll do 62 and 64. Iron rod. Initial temperature is 22.7 degrees C into an unknown water container. Unknown mass of water. Okay. Do it like this. Temperature initial. The metal is this. Temperature initial for the water is T temperature final, this is for both of them. Looking at the wrong one. 62. So you've got iron and that's essentially what we did. 66. All right. So this is what we did in lab the other day. Delta T of iron is, it's going to be temperature final minus temperature initial. Final is 59.5 and initial is 22.7. Delta T for iron equals degrees C. Delta T for water equals, initial for water was 63.2, final was 59.5. Seven.
Is this one very quick to do, the initial, is it just on the other side? Or,
Over here.
oh wait, never mind, sorry, I wrote it wrong.
Okay, so now the overall formula is the mass of the water, heat capacity of water, and delta T of water equals the negative of the mass of the iron, heat capacity of iron, delta T. This we calculated the two heat capacities that I'm representing as C there. You'll have this on the test. Specific heat capacities. Iron is 0.449 joules per gram per degree C. Water is 4.18 joules per gram per degree C. Okay, the delta T for iron was 36.8.
I have a question.
Huh?
So for delta T of water, it should still be, the temperature of the final minus the temperature of the initial. So how is
Oh,
6 degrees?
final was, yeah, I calculated that wrong. Final is 59.5, and initial for water was 63.2. So yeah, that one should have come out negative. 59.5 minus 63. So yeah, it is negative. So that's positive. Water was negative 3.7. The mass of iron is 32.5. So we have these. And then that's our X. Solve for the mass of water. What what is the mass of the water? So, $32.5. There is a negative sign here. 40.9, 36.8. Divide by 4.8, negative 3.7. So those two negative signs just cancel each other out. 32.5 times 0.449 times 36.8 divided by 4.18 divided by 3.7. So the mass of the water is 34.7.
So for the 32.5 for the mass of iron, should you put a negative in front of it, like we were writing in the C's, or just?
Say again?
For on the right side, where it says negative mass of iron, should you not put a negative in front of the 32.5?
Well, one of these temperatures, one of the delta T's is always going to come out to be negative. So that's why there's just this random negative somewhere. I could have put it over here, and it would still just cancel out. It's multiplying two negatives. But, so there'll be another negative somewhere if this cancels it out, so it comes out positive. So 34.7 grams. Yeah, just skip that calorimetry. It's essentially the same as what we're doing here. 66. Maybe I do want to do that. Okay, 62, 64. So this is thermal energy transfer. Heat going from water to metal or metal to water. 64 is 2.85 gram of lead. Lead initially at 10.3, so T initial for lead is 10.3 degrees C. Submerged in 7.55 grams of water, so I have grams of both. Initial for lead, the water initial, temperature final for both of them is what we're being asked for. And okay, C for water is 4.18. C for lead .128. So we can solve for the delta T, and then we can find the final temperature that way. So mass of lead, Cp for lead, delta T for lead equals the negative of mass, water, C for water, delta T for water. Mass of lead, 2.85. Cp for lead, 0.128. Delta T for lead, two different delta T's. We have to be able to solve for one. Did I solve this one the other day? So I guess we have to do mass of water. I guess this works. We're solving for TF. We're going to do 61, 62. It's a long walk around the book. That's water. That's what. Just don't want to do all that. Never mind that. Let's just go to 66. Heat capacity of an unknown substance. That's what we did in lab. Unknown substance. Liquid equals 1, 2. T final is 26.3. T initial of the metal is warmed to 72.1. Temperature initial of the water is 4.7. And then the water is 15.2 grams of water. What is the heat capacity of the unknown substance? So you're using that same formula. Mass of water, heat capacity of water, delta T of water equals negative mass of the metal, heat capacity of the metal, and delta T of the metal. So our delta T's are delta T for the metal equals final temperature 26.3 minus initial temperature 72.1. Delta T for the water equals final is 26.3 minus is 24.7. 26.3 minus 72.1, negative 45.8. 26.3 minus 24.7. I've got to have some of those backwards. 2.74 grams of an unknown substance, suspected to be in gold, is warmed to 72.1 and submerged into water initially at 24.7. The final temperature of the mixture is 26.3. No, that's right. Man, I'm just baiting today. Okay. Got our delta T's. All right, mass of the water, 15.2. Heat capacity of water is 4.18. It's in that chart, 4.18. Delta T of the water is 1.6. Mass of the metal is 2.74. This is our unknown. C of the metal is our unknown. Delta T of the metal is negative 45.8. I'm going to go ahead and get rid of the negative signs. So what we want is divide by 2.74, divide by 45.8. Heat capacity of the metal, 15.2 times 4.18 times 1.6 divided by 2.74 divided by 45.8, 0.81. The units here are going to be joules per mole, joules per gram. So we look at the chart. That's probably how I'll do it on the test. But this goes one step further. Could the substance possibly be pure gold? And if we look here, gold was 0.128. That's not anywhere close. All right. So I dropped those two off. And I dropped one off here too. I will get quizzes up for all of these. Unlike test 2 where I left you hanging on a couple of them, made you use the examples in the book. Next week is break, so it's 2 weeks from today. It's a test. All right. If you need to make up labs, come Monday.
You want to test?
No, I've already logged in. I haven't put them online yet, but I've got them in the spreadsheet. No.